Okay, in this chapter, I think last time we have talked about the solubility, okay, and solutions. But today we will talk about the transitions in the polymers, where we have already been talking about the glass transition temperature and melting temperatures. And I have shown you last week that how to measure the glass transition temperature. But here in this chapter, I would like to give you some more details about the transitions. Okay? This glass transition temperature actually influences the physical property of the polymers. Physical properties such as the density, free volumes, mechanical properties, despacings, and many other physical properties were influenced by the glass transition temperatures. Okay, so we will talk about how the physical property affects the transition of the polymers, and how we can measure the glass transition temperature. I think in this topic we have already been talking about it, but I will give you some more details and some more additional methods to measure the glass transition temperatures. What about the factors affecting the glass transition temperatures? Okay? We have talked about the secondary bonding forces, such as hydrogen bonding, and where my question was where this hydrogen bonding will affect glass transition temperature or melting temperatures. Okay, so I will talk about several factors affecting these transitions of the polymers. First of all, glass transition temperature of the glassy polymer, such as polymethyl methacrylate or polystyrenes, are regarded as a very hard material at room temperature. Okay, at room temperature, these materials are pretty glassy, okay? Pretty easy to be broken. Okay? Therefore, TG, glass transition temperature of these materials should be above the room temperature. Okay, so higher than room temperature. Okay, however, if you think about the rubbery materials such as polybutadiene, polyethylacrylate, methacrylate, sticky material, the Scotch tape, rubbers are at room temperature. These are regarded as a rubbery material, flexible material. But if we cool down, okay, if we put this rubber into the liquid nitrogen, okay, temperature of the liquid nitrogen is minus 190 degrees C. Okay, so if you put this rubber into the liquid nitrogen at minus 190 degrees C, and you will easily break these materials, because at that low temperature, these materials are rigid material. Okay? So rubbery material depended upon what kind of temperature that you are talking about. Okay? Anyway, at low temperature, most of the amorphous polymers are very stiff and glassy, and sometimes it's regarded as inorganic polymers. But if you heat it up, the materials, then polymers will be very flexible, will be softened, so that it will become rubbery. So rubbery versus the glassy depended upon the temperatures that you are talking about. Okay? So the TG is a temperature at which the amorphous polymer portion is melting. Okay. Now I told you that melting of the amorphous portion is regarded as a TG, and it's not the exact definition of the glass transition temperature. But I would say that melting temperature TM is what? Melting temperature is defined as the temperature at which the crystalline portion is moving, is melting, right? But the glass transition temperature is the one that you have just opposite to the melting temperature. You can remember that glass transition temperature is the temperature at which the amorphous portion is melting. And it's not melting actually, but it's moving. Amorphous portion is quite moving at the temperature. Okay? Easy to remember. Okay? TG, therefore, constitutes the most important mechanical property. So mechanical property will depend upon the glass transition temperature of the polymers. If you have a high TG material, this material is very, difficult to be broken. So you have a very high mechanical properties, okay, of these materials. High TG material can be made by adding the benzene ring in your backbones. Okay, so if you have a very aromatic rings in your backbone, your TG will be much increased because of the non-flexibility of this six-membered ring, and also very flat benzene ring, so they can pack together, and the density will be much higher. These all contributed to the high increase of the glass transition temperatures. In the meantime, if you have the aliphatic chains, like a C carbon and carbon chains, those carbon and carbon chains will be moving, and it's rotating, so that the flexibility of this aliphatic chain versus the aromatic chain decreases the glass transition temperature of the most materials. So if you look at the backbone of the backbone structure, chemical structure of this material, you can imagine the glass transition temperatures. That's why I have emphasized to remember about the chemical structure of these materials. Well, we have this type of peak. Last time I think you have seen the DSC, you have seen the GPC in the laboratory, but I have shown you the instrument called the Dynamic Mechanical Analyzer, DMA, at the same room. Okay. Now DMA, Dynamic Mechanical Analyzer, I think you will see this instrument in a few minutes, but it detects the as you increase the temperature, it detects the modulus. Detects the modulus, which is the loss modulus, but modulus E decreases in all cases as you increase the temperature. Okay? Now, modulus is higher at low temperature for semi-crystalline material and amorphous materials. And the upper curve is the semi-crystalline material. This is the amorphous materials. And the drop of your first transition curve is called the glass transition temperature. Okay? So there is something happen between the glassy state versus the rubbery states. Okay? The final point here is called, in many cases, the melting points. Okay? Melting points. And this is the glass to rubber transition points. So you can detect the glass transition temperature by using third method, which is dynamic mechanical analyzer. Okay? First method of detecting your DSC, the TG is what? DSC is the first method, and the DMA is the second method, and perhaps you can detect the TG by dynamic thermal analyzer, DTA. So I will explain in all those three methods in a minute. Okay. Now, first of all, these are the amorphous region, and amorphous regions of the material begins to exhibit the long-range interactions. In other words, at low temperature, you have a long-range interaction, meaning that the chain-chain interaction is much more important in many cases. And so that if you think about your tree, okay, when you have a wind, the trunk will not be moving at low speed of your wind. Okay. However, if you increase the wind flow rate, your leaves might moving. Okay. Leaves could be regarded as a side chain, or could be regarded as some portions in a long distance. In other words, if you look at the space, your material will be located in a space, and some of those material might be moving. That's what we call the long-range interactions. Okay? If your chain is moving very rapidly, we regard it as short-range interactions. Okay, so short-range interaction versus the long-range interaction might be a little different. Okay, anyway, in amorphous region we have long-range interaction, or the segmental motion. Segmental motion is the one that segment is regarded as perhaps several repeating units. Okay, several repeating units. You know the repeating units, and if you have about 5 to 10 repeating units, we call this as a segment. Okay, as a segment. So segment is not a definite term, but it's kind of the indefinite term. So just like a several. Okay, just like a several. Several is not a definite number, but it could be regarded as a 5, 4. Anyway, that's something like that. So a segmental motion is the one that you have some motions, but it's regarded as a long range cooperative segmental motions. So this molecular motion is available to the polymer chain below the glass transition temperature, and this is restricted at below the glass transition temperatures. However, if you increase the temperature, the thermal motion increases the chain interactions, so that these cooperative rotational motion will be available, and so that the material will be flow upon applying the stresses. So above the glass transition temperature, you can detect the short-range interactions, meaning that your segment will be moving, enormously. Therefore, you increase the free volume and decrease the modulus. Okay? This is the brief description of the glass to rubber states, and so that for semi-crystalline materials, you can detect the glass transition temperature. First, the transition from high modulus region versus the low modulus region, and the midpoint is regarded as TG. Okay? If you have amorphous polymer, your modulus will be much, enormously decreased, because there is no crystalline portion in amorphous polymers. If you have a cross-linked polymer, you do not detect any melting temperature, so that it will just stay right there. However, if you have a non-cross-linked polymer, you can detect the degradation. Okay? It's not melting, but it's degradation. If you have some crystalline portion, of course, this could be a melting temperature. But if you don't have any melting portion, then this could be the composition temperature. So depending upon whether you have your crystallinity, this temperature is a little different. High molecular polymer versus the low molecular polymer have a little different, the final, the decrease of temperature. But anyway, we can detect the TG in the middle of this, two transition regions of your modulus. Okay? So this is the easy way of detecting the transition temperatures. Now, how we can detect the TG can be described here. I know that you have already been, we have already been discussed about the DSC. Okay? DSC is very similar to DTA, but what they have is they have a two-chamber. They have one chamber, but with two adiabatic chambers, and they have the thermocouples just beneath the sample pans and the reference pan. Reference pan does not contain any samples, but polymer pan contains several milligrams of the polymer samples in here. Okay? This picture is not exactly the same, but I think that one of this sample pan, one of this reference pan should be empty, and the second one should contain the polymer. Okay? Now, if the polymer undergoes the exothermic, thermal transition, then then temperature of the sample pan decreases because heat will be excited from the sample pan to the surroundings. In that case, the reference pan detects the temperature, and this controller will apply the heat to balance the temperature between the sample pan and the reference pans. And this way, I think they can detect the exothermic reactions and the endothermic reactions. Now, this DTA is, as it says, it just detects the temperature of sample pan and the reference pans. Okay? And this is what they call is a differential thermal analysis. Now, DSC is differential scanning calorimeter. Okay, differential scanning calorimeter, and it's very similar to DTA, but a little different in terms of the heat balance. Okay, in other words, DTA just detects a temperature difference between the sample pan and the reference pan. Okay, but DSC supply the heat of those lows, so that DSC measures the difference in the heat flow rate rather than temperature itself. That's why we call this as a calorimeter, the scanning calorimeter, whereas DTA is a thermal analysis, differential thermal analysis. Just it detects the temperature below or beneath the sample pans and the reference pans. Right? Principle is about the same, but the difference is that whether you supply the heat or not. In this case, DTA, you do not supply the heat, just detects the temperature differences. Okay? Whereas DSC detects the temperature and supply the heat, okay? Supply the heat to the sample pan, or supply the heat to the reference pan, depending upon whether you have exothermic reaction of the sample or endothermic reaction of the samples. But DTA is widely used in the ceramic materials, whereas in the case of polymers, DSC is very widely used. Okay, so if you have any choice in detecting the glass transition temperature, you better use DSC. That's why we have a DSC here in this floor. Okay? So DSC is much more versatile in detecting the thermal transition of the polymers. I think we have already talked about these graphs. If you have an endothermic heat flow or exothermic heat flow, and DSC measures the endothermic versus the exothermic, and you can also detect the other parameters such as the heat capacities of the materials and oxidative stability or reaction kinetics using this DSC. And this is the typical DSC transition curve where you have movement of your amorphous portion, so that your chain moves, particularly the side chain moves, so that it undergoes the endothermic reaction, and your polymer melts if you have crystalline portions. And if you decrease the temperature, then your polymer will become crystallized, and crystallization means that your heat is exerted from your system to the surroundings, because your polymer will be organized to have a high density, so that the extra heat from your system will be going out. That's why we regard this as an exothermic reaction. And melting is different. Melting is opposite, because your crystalline portion will be moving, so that in order to move those crystalline portion, then you have to absorb your heat from outside or surroundings to the systems. Anyway, this transition is very typical so that you can detect the glass transition temperature of the material using the DSC. Okay? Now, most of the polymer are very sensitive to these heat flows. However, in some polymers, it's not easy to detect the heat flow using this DSC. Okay? Particularly, if you have aromatic rings in your chains, it's not easy to detect those glass transition temperature using the DSC in this case. So this is a typical DTA and DSC images. This was a very old model, but we have new models as I showed you, last time. The third method of measuring the glass transition temperature is by using the DMA, dynamic mechanical analyzer, which I have just shown you and also described you. This is the sample pan where you put the film in the two jug so that you have your film samples and you vibrate them. Okay, if you vibrate them, oscillations. Okay? Now, oscillation or amplitude or amplitude of the oscillation is called the theta or delta. Excuse me, I think this should be theta. The angle, amplitude angle, and by measuring the modulus, which is described as the storage modulus and the loss modulus. Storage modulus is the modulus where you have your energy is stored, whereas loss modulus is described as the energy that is dissipated from your system. By measuring the angle and modulus, which is a storage modulus and loss modulus, you can measure the E prime and E double prime. Okay, E prime is the storage modulus, and modulus, as you recall the Young's equation, the stress is equal to modulus times strain. Okay, right? If you look at the spring, and the E is a spring constant, but in this case, it's not just the flow in one direction, but it's oscillation. So oscillation amplitude should be considered, and if your amplitude is in the cosine curve or sine curve, and those determines the storage modulus and the loss modulus. Now tan delta is the ratio of your loss modulus versus the storage modulus, and loss modulus versus the storage modulus. And tan delta is the measure of the glass transition temperature as well. Anyway, if you apply the amplitude of your sample film, okay, and your modulus, and you increase the temperature, and your modulus will decrease, right? And the pattern that I have shown you is something like this. This is the storage modulus is pretty high at low temperature, and it decreases, and may undergo the glass transition and the melting, which I have shown you in your previous slides. But however, the loss modulus behaves a little different than the storage modulus, and the tan delta, whereas the ratio of the E double prime divided by the E prime is something like this, which is very similar to the derivative curve of your system. Now, the maximum point here, maximum point of the tan delta, or the midpoint between the high modulus and the low modulus, whereas this point is almost the same, and this is regarded as a glass transition temperature. Okay? So, the DMA, dynamic mechanical analyzer, is much more sensitive to measuring the glass transition temperature than the DSC. Okay, so DMA is much more versatile than DSC instrument. Okay? Anyway, you can detect the TG by DSC and DMA, and of course, by changing the amplitude, if you have a high speed, a high amplitude or low amplitude, and also the rate of increase of your temperature. In other words, if you increase the temperature of your whole system 10 degrees per minute, or 1 degree per minute, or 50 degrees per minute, determines the movement of your cross transition temperature as well. So you have to identify, you have to tell which condition that you have used to detecting the cross transition temperature of the systems. Anyway, DMA is a very powerful tool in measuring the cross transition temperature of your systems, particularly the high modulus polymers. If you have a very high modulus, it's not easy to detect the cross transition temperature by DSC, but DMA can detect. Okay? DMA can detect the cross transition temperature here, whereas below the cross transition temperature, you may have some transitions as well. Okay? Now, the modulus might be linear, but it's decreasing. This might be some other transitions. Okay? Some other transitions, and this is the primary transition. That's why they call this as alpha transition. Okay, alpha transition, and they may have some transition which is called the beta transition or gamma transition. Okay, and these transition might be different from cross transition temperatures. Okay? So the alpha transition is a gradual main chain transition, as you can see here. But if you have a little bit of side chains, then you can detect as well. You have a bending and the stretching vibrations, or the local motions. You can detect those transitions as well. So the TG is regarded as amorphous portions. The melting of the amorphous portion, that's what I've said to you. And it's a gradual main chain transition, whereas side chains, or such as leaves, might move. Okay, that's why you increase the free volumes, and perhaps this tool, this DMA, can detect the very, very sensitive regions as well. This is another description of the DMA curves. You can find out those properties and so on. So this is the main. You can easily see that this is the TG. This side chain groups might move, or bending, or local motion, and those were regarded as TG and alpha transition, beta transition, stuff like that. So in summary, TG in detecting this by DMA, TG is alpha transition temperature. You can detect the beta transition due to the side chain, and gamma transition, and others by using the DMA. Whereas if you use a DSC, you can only detect the TG, but not the beta transition or gamma transitions in DSC measurements. Okay, I have introduced to you three methods in measuring the cross transition temperatures and the transition at the glassy state. Okay? We can talk about the cross transition temperature in terms of the free volumes. Last time I showed you that as you increase the temperature, your side chain will move, right? Side chain will move. And also, if you as you further increase your temperature, your main chain may move. Right? If your main chain will move okay, you need extra volumes. Okay, if I'm moving in this way, I need some extra volumes to move, right? So my space at a given state in the space is much more larger than the space at low temperature, right? So at low temperature, I need just about this space at a frozen state, right? But at high temperature, I need some more volumes where I'm not occupying this volume that I'm moving. Okay, if I'm moving at a frozen state, I need this volume, but at high temperature, I need extra volumes, right? This volume, unoccupied volume, is regarded as a free volume, but I need a volume because I need that state, right? So the shaded area is regarded as free volumes. Now you remember that your specific volume V increases as you increase the temperature, right? And there is a transition point between the glassy state and the rubbery state, right? The transition between the glassy to rubbery is called the glass transition temperatures. Now, when I look at some temperature, such as if TG is 35 degrees C, okay, and I'm looking at this material at 80 degrees C, okay, another 45 degrees C higher, I'm in the rubbery states, right? And I can expect that I have a little bit more free volumes. Now, that 85 degrees C might be here. If I further increase the temperature, like 120 degrees C, my backbone, of course, and I need more volumes. Okay. Now that temperature might be right in here. So now, depending upon the temperature, your free volume might be different. Okay. Delta V might be different. There are very well-known chemical engineer, Williams, Ferry, and Landell described this type of phenomena as free volumes. Okay? Free volume, therefore, VF is defined as specific volume of the polymer mass V minus the volume of the solidly packed molecules. In other words, if this V is the V right in here at a given temperature, okay, at a given temperature, and the Vs might be the one that could be expected from this line, glass line. Okay? So this difference is called the free volume, and the total free volume is called the shaded line, okay, right here. Okay, so free volume at a given temperature is V divided by V minus Vs, but total free volume is this shaded line, as you can see here. So according to their definition, the free volume fraction can be described as some temperature above the transition temperature, T here, minus Tg, and volume fraction here can be correlated each other with some constants A and B. And A and B that they have detected with several systems could be in this number. This is the according to their experiments, okay? According to their experiences. Anyway, free volume. If you have a high free volume polymer can be synthesized or designed in such a way that if you have a larger the temperature, if you have a high glass transition temperature polymer, then you can expect that you have a high free volumes. And I have described this in one of the articles last year in Science, that if you have a rigidity in your polymeric system, then you can expect to have a high free volumes, so that through this high free volume, you have a lot of gas molecules penetrate through. Okay? That's one of the articles that I have described last year. So polymer rigidity improves the gas permeation, and you can also study about this type of phenomena as well. So free volume can be influenced by the cross transition temperature of the material or affecting the cross transition temperatures. Second aspect about the factors influencing the cross transition temperature is attractive forces, okay? Such as hydrogen bonding or interchain interactions. If you have dipole-dipole interactions, such as PVC or the polyacrylonitrile or the acrylic acid, okay, they have hydrogen bonding or dipole-dipole interactions. And if you have those dipole-dipole interactions and polar bonding, you can expect to have high cross transition temperatures. Higher cross transition temperature than the material without any of these type of attractive forces. Okay? So high attractive forces increases the cross transition temperature. What about the mobility? Okay, mobility. If you have high mobility, then you're expecting to have a cross transition temperature, to be lower. Okay? Now I can say that if you look at the polyethylene, okay, polyethylene as an example, versus the PTFE. PTFE is a polytetrafluoroethylene. So in place of hydrogen, you can replace hydrogen with the fluorine groups. Now fluorine is much larger than hydrogen. Okay? So if you have a larger substituent groups in your carbon group, then carbon-carbon rotation is quite restricted. It's not easy to rotate because of the larger substituent groups, right? So the rotation is quite restricted in the case of PTFE than polyethylene. So polyethylene is much more flexible than PTFE. PTFE, because of the restriction in the rotation, it represents a high cross transition temperature than the polyethylenes. Okay. But if you compare the polysiloxane, siloxane, polysiloxane versus the polyethylene, polysiloxane, PDMS rubber, silicon rubber, polydimethyl siloxane is much more flexible than polyethylenes because the polyethylene can be packed each other, okay? Because of the crystallinity, the Tg is much lower in the case of polysiloxane than the polyethylene. So the mobility, internal mobility, internal mobility is increasing as you increase from PTFE to the polysiloxanes, and the potential energy is, of course, reverse opposite to this flexibility. So if you have high potential energy, you're expected to have a restriction in the freedom, whereas if the potential energy is lower, that means that the material is much more flexible. Okay? So the Tg depended upon the mobility, okay? Opposite to the mobility in this case. Interaction. This is the interactions. Interaction doesn't really matter. Okay. It doesn't have any correlation in terms of the cross transition temperatures. What about the rigidity? What about the stiffness of the materials? Okay. If you have I told you that if you have a very highly rigid material, then you expect to have a high grass-transition temperatures. Okay, mechanically stiff material should have a high TG. Okay, in this case. Now, mechanical strength can be detected, as you can see here, depending upon the Young's modulus. You serve the less time in the laboratory that you have a machine that you can stretch your films or stretch your materials. If you think about your spring, modulus is the constant where your stress versus the strain is correlated, and you can detect the Young's modulus. Now, Young's modulus is different from storage modulus because you have different mode of your mechanical stress. Because this Young's modulus is applying your stress in the tensile mode. Okay, you apply the stress in one direction, whereas the storage modulus apply the stress in the oscillation mode, right? So you have two different modes of modulus. Now, Young's modulus can be detected by stretching your material. Okay? Anyway, you looked at this modulus. As you increase the temperature, modulus decreases, right? And the volume increases. Now, if you have a high volume polymer, then you have a high free volumes, and the modulus, of course, will be decreasing in this case. What about the molecular weight? Molecular weight actually can influence the glass transition temperature a little bit. Right? If you think about the number of the methylene units here, your TG will increase in the example of the polyphosphagen polymer. This polymer is called the polyphosphagen, and polyphosphagen has carbon and hydrogen and oxygen and nitrogen, and those atoms like a CHON are regarded as organic atoms, organic materials, whereas phosphorus is regarded as inorganic material. So this polymer is very unique, where this polymer is regarded as organic and inorganic polymer. Okay. I'm telling you many examples of the organic polymers, but inorganic polymer or organic inorganic polymer are the very unique nature and type of the polymers in the future. Now, polyphosphagen has very unique properties, and it has been developed by Professor Alcock at the Penn State University a long time ago, back in the 60s. But he has been working on this polyphosphagen for the last 50 years. And some of this polymer backbone is the same, but just changing these side chains. And he has a variety of polymers, maybe hundreds of polymers. You can put the methyl group here, ethyl group, propyl group, octyl group, or benzene ring, okay, and phenyl ring or whatever, okay? Or naphthalene rings. And he has many types of polyphosphagens. Anyway, by changing this side chain length, okay, if you change this side chain length, your TG increases in many cases. Okay? So TG depended upon the side chain length as well. And he described that TG of given the length of the side chain can be described as a TG of the infinite molecular weight and infinite side chain minus the chain length of this material. X could be chain length, I guess. And also the polymer, the TG might be influenced by the mass of the polymers, molecular mass of the polymers. In other words, if you have higher repeating units or high molecular weight, your TG, which is the glassy to rubbery transition, increases as you increase the molar mass. In both the amorphous polymers and the crystalline, semi-crystalline polymers, up to some points, okay? Up to some points, but it reaches a plateau regions. Now I'm not go in more details about this, the phenomena, but this is almost the same for amorphous polymers and the semi-crystalline polymers. TG of the several nylons can be described here in these slides. Now I have a nylon 6, nylon 11, nylon 12, and polyethylenes. If you remember, this number, how we can put this number, depending upon how many methylene units you have in between the amide groups, right? If you remember about this chemical structure, you have a carbonyl, CO, and NH. CONH is the amide group, right? Amide, the functional group. And in between this carbonyl and NH, you have methylene units, CH2 units, and CH2 times X. In the case of nylon 6, what is X? 6? Should be 5, right? Should be 5. So carbonyl should be included in the number, in counting your number, right? What about nylon 11? 10, right? 12 is 11. What about 4? You have a 3. Now, so you all know that how we can name these nylons. Now, between this carbonyl and amide, NH imide groups, you have a smaller number in the methylene units and longer methylene units. If you have a smaller in number, like nylon 4, what happens is that you have a carbonyl and the NH group, which may have a hydrogen bonding with each other, right? Chain to chain, interchain hydrogen bonding versus the intramolecular hydrogen bondings. So if you have within a given length, if you have many amide groups, you are planned to have a much more higher density of the hydrogen bonding, whereas if you have a longer nylon number, right, such as nylon 12, you have too many methylene units between the amide groups, so that your hydrogen bonding force, bonding interaction is less as you increase the number of your nylons, right? So melting temperature decreases. Melting temperature decreases as you increase your number of nylons because of the less hydrogen bonding due to the low number of carbonyl groups, low number of the NH groups within a given length, right? So therefore density decreases. Okay, density is defined as how many molecules you have within a given space, gram per cubic centimeter, right? Mass per volume. TS is a tensile strength. Tensile strength is the one that if you have a higher modulus material or tensile strength at break, its material is much more stronger. If you have a higher hydrogen bonding forces between the chains, low number in the nylon, you have a high melting point, high density, high tensile strength, and high water content, because you have a high density of the carbonyl and NH groups. Carbonyl and NH group can have a hydrogen bonding with water as well. Therefore, your water content is much higher compared to other nylons, right? If you think about the polyethylene, the water content is negligible. It's not measurable because there is no site for hydrogen bonding in there. Okay? Well, you may have a very small amount of water in polyethylene, but it's not detectable. So all of those, the cross-transition temperature in nylons versus the polyethylene depended upon hydrogen bonding forces. And how many sites for hydrogen bonding is available in your polymeric units as well. Second example is in the same analogy, and if you look at this is the polyamide, the nylons. Polyamide have a carbonyl and NH group. Carbonyl can be detected at usually if it's an ester group, ketone group, the carbonyl in ketone can be detected at 17, 15 reciprocal centimeter. If you have an ester group, it should be 1735. But if you have a hydrogen bonding, then it moves to a lower frequency region, which is 1650. This is 1550. What about if you have one more oxygen to carbonyl? This is what we call urethane. Okay, urethane. And you have urea. If you have one more NH group, this is called urea. Urea, amide, and urethane. Urea has one more hydrogen bonding sites compared with the polyamide. This ethyl group contributed to the rotation. Okay, if you have it contribute to the more flexible units. Flexibility gives you a low melting point compared with the polyamide. If you have one more site for hydrogen bonding, they contribute to the high melting points. So melting point of polyurea is much higher than PA. PA is higher than the polyurethanes. So polyurethane can be made for 쫄바지, flexible, right? Because of the flexible ether groups. Whereas polyurea can be a very highly melting resins so that you can make it as a food tray. 식판이라고 하나요? 식판 같은 거. So you can make a food tray with high melting point polyureas. Polyamide can be made for plastic, or could be made for fibers, semi-crystalline fibers, and so on. Anyway, in summary, if you have hydrogen bonding forces, then you increase your enthalpy of melting, and so that you contributed to the high melting temperature. If you have a swivel group, such as ether, then it contributes to the flexibility so that the melting point decreases compared with the polyamide. Okay. Finally, I just wanted to show you this graph here. And usually, if you increase the temperature, it follows the solid line starting from number 5 region. Okay? So the solid line, if you increase your specific volume, and the rate of increase is different as the glass state turn into the flexible rubber state. Okay? So your slope is different. So this inflection point is called the glass transition temperature. Okay, again. At some point, the solid polymer, although it's flexible, will melt if you have the crystalline portion. So melting will give you system, with the abrupt increase your specific volumes. So polymer in the solid phase will become liquid phase, okay, as you increase the temperature of a certain temperature. So think about your film. For example, a semi-crystalline film will undergo from state 5, increase the temperature to 4, further increase the temperature, will become number 1 state, which is in a molten state or melt state, right? So your material is melt, liquid phase. And you melt your polymer in an oven, okay, in the oven, and you can slowly cool down your polymer in the oven, okay, and it follows 4 and 5 if it's a very slow cooling, right? And if you increase the temperature, then it follows this solid line, slowly cool down, it comes down here. However, in the state number 1, if you just open the oven at high temperature, take out the liquid sample, put it at the room temperature or put it at the liquid nitrogen, what happened? Does it follow the same line as 1, 4, and 5? No, it's not. Actually, it's written in here. It follows, upon very rapid cooling, it follows this dotted line here. Because there is no time to cool down and put it into the, to become the original state of, volumes. So it has excessive volume, specific volume, and following this number 3 and number 2. Okay? And, okay, at room temperature, let's say that this 5 and 2, this state is room temperature. At room temperature, you can make 2 different polymers, 2 different shape of the polymers with the same chemical structures. Rapid cooling or slow cooling. If you have a rapid cooling of your material, you have a little bit of excess volumes in state number 2, which is different from state 5. Okay? What happened? In state number 2, what happened if you heat it up again, your material, what happened? Does it follow this 3 and 1, or does it follow the other route? Is my question. What happened? Other routes. Tell me how you think about this material. So you are in the state number 2, and you heat it up with the heat gun, hair dryer. You heat it up. Your film, which was already been rapidly cooled, and heat it up with the heat gun, very rapidly heat it up. What happened? Same route as what? 3 and 1. There's one question, one answer. But any other answers? Tell me. Please speak up. 5, 4, something like that. So that's the second route. What else? 2 and what?
Other.
Tell me the number. More what? This way? It comes like this. Then 3. It may go well. It undergoes within these numbers. So there are 2 routes. What else? Tell me. Tell me the third route.
2, 4, 1.
2, 4, and 1. Yes. Well, okay, that's also possible too. Okay, okay. Anyway, he changed his mind. First root is 2, 3, 1. Second root is 2, 5, 4, 1. Third root is 2, 4, 1. Okay. Any other answers? Well, actually, if we increase the temperature from this state, which is over the expanded state, actually it follows number 2 root. It decreases the temperature. I mean, it comes down. In other words, rather than expansion, if you increase the temperature, usually your material will be expanded, right? But because it was over the metastable state, it comes down to the stable 5, and then follow this 4 and 1 line here in this case. It's also possible that it comes down something like this, but it's, well, anyway, that it could go down to 5 and 4 depending upon the rate of your heating. It does not follow metastable 3 and 1 state. Okay? So the answer might be 2 or 3, okay? Depending upon your state of your material. With this principle, you can make a film with shrinkable films, heat shrinkable films. If you heat it up, most of your film will be expanded. But some films, if you heat it up, your material will be shrunken. This is how you make this film, and this film can be applied to your. If you look at the heat shrinkable film in the winter, you can put the film in the window to protect your room from the outside low temperature, cold temperature. And if you apply the heat gun, it will be very much shrunken so that it will be very flat instead of flexible films. Okay? It will be very flat films. If you look at the bending machines, the guys will take the Coca-Cola or those soft drinks, and these soft drinks are stored in a box, or could be wrapped with a film. Those film will be tightened all of your shapes, and this is how they wrap it up, soft drinks. In other words, if you have a soft drinks, they wrap it up with the film and apply the heat guns so that it will be packing up those cans. and in many industry, they use these heat shrinkable films, heat shrinkable tubes as well. Heat shrinkable tubes. I lost my heat shrinkable tube because I just wanted to show you about this principle, but I lost the box. If you wanted to connect 2 lines, okay, what usually you do is you just connect your copper wire, okay, copper wire, and then wrap it up with the tapes. But at hot temperature, in the summer, this tape will be delaminated, so that there's a lot of questions about this. Instead of insulation tapes, if you apply the heat shrinkable tube, what you do is that you just connect. Before you connect, I think you can just put your heat shrinkable tube in one of this portion, and just to connect them, and slide this heat shrinkable tube in the connected sides and heat it up. They will just shrink those portions without any delaminated defects. So heat shrinkable tubes and heat shrinkable films can be made by using this principle. I'll just skip this. Finally, I can show you the Fox equation calculating the copolymer systems. Copolymer systems. If you have polymer 1 and polymer 2, and if you know the glass transition temperature of polymer 1 and polymer 2, and if you know the mixture of weight percent or mole fraction of those polymer 1 and polymer 2, you can calculate the glass transition temperature of the copolymer. Okay? Copolymer means what? If you have one monomeric units and the second monomeric units, put it together in chemical reaction, then we call this as a copolymers. If you have a top polymer systems, you have 3 components. So then you can add W3 divided by Tg3, and so on. Okay. So if you know the portion of polymeric units of each portion and glass transition temperature of the pure polymer or homopolymer, then you can calculate the glass transition temperature using this Fox equation. Remember, however, you should be very careful in calculating this glass transition temperature of the copolymers. This T should be in Kelvin temperature rather than, Celsius or Fahrenheit. If you put the Celsius and Fahrenheit, you have a different number. You'll end up with the different numbers of the polymers. Please convert. If you are given of Tg1 as a Celsius, you have to convert into a Kelvin temperatures. Okay? Okay, I think you can Tg and Tm. So this is all that I can say about the chapter 7, about the transition of the polymers. Any questions or comments?
TM이 낮아지면 TG도 항상 같이 낮아지나요?
The question was whether Tg and Tm might be moving up in proportion to the decrease of Tm and Tg. Well, sometimes sometimes it moves with the same portion, sometimes not, depending upon your crystallinity, depending upon your amorphous portions.
이게 아까 나일론 이 방법 개수로 하는 이 방법이 TG도 같이 할 수 있나요?
Well, the question was, I think I'm talking in English because of the audience. That's okay, I can translate them. In the case of nylons, whether we can detect whether we can predict the glass transition temperature rather than melting temperature in terms of the number of methylene units. Well, I cannot say that the glass transition temperature might be correlated with the number of methylene units, but I can say that yes, it could be possible to predict the Tg as well.
Yeah. Thank you.
You're welcome. Any other questions? If not, I think we can talk about chapter 8 on Friday. Chapter 8 is related with the polycondensations. So we will talk about this polycondensation. And I will give you the real polycondensation reactions. Please read about this chapter, and this is the main portion of the this course. Okay? Polycondensation and chain growth polymerizations. Chapter 8 and chapter 9 is a main core part of this chapter, this course. So we can compare the chain growth and stack growth polymerization as well, starting with the several aspects. So please read about this chapter as well. So I will see you on Friday. Okay. Thank you.